In this video, we are going to discuss about aromatic nucleophilic substitution. You may know that aromatic ring, for example benzene, it is nucleophilic in nature because of the high electron density. So I say this is Nu minus. To this, I cannot add another nucleophile because both carries negative charge. They won't react to give the product. So how are we going to carry out nucleophilic substitution in aromatic ring? So this video is about that. There are three techniques, three methods to introduce nucleophile to aromatic ring. That is like Cl minus, F minus, amine, alcohol. They can be introduced to aromatic ring by three methods. First one, via diazonium salt. Second one, via benzene. Third one, via aromatic nucleophilic substitution. We call it SNAR, aromatic nucleophilic substitution. This reaction is also known as addition elimination mechanism. The benzene mechanism, it is known as elimination addition. Now let's see one by one. First one, it is diazonium salt. When you add nitrous acid to aromatic amine, not aliphatic amine, when you add nitrous acid, that is HNO2, to aromatic amine, what we get is N2 plus Cl minus. But this nitrous acid is not that much common. So what we do, we generate nitrous acid in situ from sodium nitrite and HCl. If you mix this salt and HCl acid, they will react to give nitrous acid. The nitrous acid reacts with this amine to give diazonium salt. This Cl comes from this one. This very old method. Nowadays, instead of nitrous acid, what we do is we go for organic nitrite. That is RON double bond O. Organic nitrite we use. In that case also you will get diazonium salt and the further reaction will be same. So this may be the modern method. The reason why we go for this is when you go for NaNO2 and HCl, this reaction should be carried out only in water because this salt, it will be soluble only in water. Because of that, you cannot add some strong nucleophile to this, or you cannot add another nucleophile which is insoluble in water. When you go for this organic nitrite, you need not add water and you can carry out that in organic solvent. So that is why we go for this one. This one, it is aqueous solvent. So water, but this one organic solvent. Once you have generated the diazonium salt, I write like this, it may be somewhat clear. So here it is plus and Cl minus. Nucleophile can easily attack here and displace that. Usually it goes through radical mechanism. It forms radical which adds with other halogens. But even write like this you can write. So easily you can remember. For example, if I add CuCl, cuprous chloride, the Cl minus will displace this to give the corresponding halogen. Sorry, if you add CuCN, the Cn minus will displace to get Cn. Similarly, if you add CuBr, you will get aryl bromide. So these reactions, in these reactions, you have attached Cn minus, Cl minus, Br minus, not electrophilic halogen. The same compound you can prepare from benzene by adding electrophilic bromine atom. But in this I have not added electrophilic, it is nucleophilic, that is Br minus I have added. The earlier case it will be bromine, in that Br plus will be there, that will add to the benzene. But here Br minus has added to the benzene ring. So it is nucleophilic substitution. Apart from that, I can also convert this diazonium salt to fluorobenzene. You cannot obtain fluorobenzene by aromatic electrophilic substitution. You can go for bromine and iodine. Chlorine itself, it will be somewhat difficult, and in the case of fluorine it will be highly difficult. But by this method, just decomposition of this diazonium tetrafluoroborate, you will get the fluorobenzene. The fluorine comes from this. Just you have to bring that solution to room temperature. It will decompose to give N2, BF3 and fluorobenzene. Next one, if you don't add anything to the diazonium salt, the water, whatever is present in the solution, this itself can displace to give phenol. So generally these reactions don't find much application in the synthesis because the corresponding alcohol, it is very easy to get. Apart from that, one more reaction, that is, can I remove this N2Cl and introduce H there? That is, can I convert that into benzene? Basically I remove NH2 from the aromatic ring. So convert that into diazonium salt and then remove that. It is possible. So for that we add hypophosphorus acid, H2PO3. If you add this, not phosphoric acid, hypophosphorus acid, if you add this, then it will get converted to benzene. So generally this technique is used to remove nitro group from aromatic ring. If there is nitro group, there is no other method to cleave this bond. We reduce that, we convert into amine. The amine is converted into diazonium salt. Then in situ, if you add H2PO3, you will get this NO2 removed. So for the reduction, generally we use palladium charcoal or tin HCl. These two are the very popular reducing agent. Recently, I came across one more reaction, that is Mirwin reaction. This diazonium salt, if you add acrylonitrile in the presence of catalyst, maybe copper catalyst, what we get is a product like this. So this adds here to give this product. So basically it looks like Michael addition. So this molecule undergoes Michael addition type reaction. So this is called Meerwein reaction. Second one, it is SNAR reaction. Already I have mentioned that aromatic ring, it is nucleophilic. It cannot react with another nucleophile. But if you attach some electron withdrawing group to this, like nitro, because of resonance, what happens? We get a structure like this. So there is plus charge in the ring now. As such, there is no positive charge. But when there is resonance, because of this electron withdrawing group, the electron density from this is removed by electron withdrawing group and we get positive charge. Now this positive charge can be attacked by another nucleophile. For example, say I have attached a nucleophile. So already there is one hydrogen atom. So I write that also. Now when it comes back, there are two possibilities. The hydrogen may leave or the nucleophile which has added that may leave. So say this possibility 1, this is possibility 2. If the nucleophile leaves, what we get is this one, the same intermediate. That means basically there is no reaction. If the hydrogen leaves, then it has to go as not proton, H minus hydride. So H minus has to leave. H minus cannot act as a good leaving group. So in only one reaction we come across H minus, that is Cannizzaro reaction, in which H minus is the leaving group. Except that nowhere we come across hydride as leaving group. So this won't act as leaving group. This will act. So what we get is no reaction. Instead of that, if I introduce some leaving group here, for example, I go for X halogens. Here say nucleophile I have attached. When it comes back, X minus is a better leaving group than nucleophile. So what we get is a product in which we have the nucleophile. If you observe carefully, first the nucleophile adds here. So the first one is addition. Then afterwards the nucleophile leaves. So that is elimination. That's why it is called as addition elimination mechanism. Now there are few points to note in this mechanism. Instead of NO2 in the fourth position to X, if it is in the third position, because of resonance we won't get plus charge here. We get plus charge only in the ortho and para position, not in the meta position. As a result, the del plus on this carbon is very less compared to this. So nucleophile cannot attack here easily. On the other hand, if it is at the para position or the ortho position, there is plus charge, so it can be easily replaced. This is the first point. Second point, instead of one NO2, if I attach one more NO2 here, Now, because of 2 NO2 group, the plus charge on the ortho position to this and para position to this, it will be very high. So this will react very fast than this one, with only one nitro group, because the positive charge on this carbon is very high. The third point is, in aliphatic nucleophilic substitution, iodine is a better leaving group than bromine. Bromine is a better leaving group than chlorine. Generally, fluorine, it doesn't act as leaving group. So this is the order. Iodine is a better leaving group than bromine, than chlorine. But in the case of aromatic nucleophilic substitution, this order is reversed. Fluorine is a better leaving group than chlorine, bromine and iodine. What is the reason? It is nothing but, when there is fluorine, since it has higher electronegativity compared to other halogens, this also contributes to some extent the positive charge on the carbon atom. In addition to NO2, this also pulls the electron in the bond. As a result, the positive charge on the carbon atom is more. So that is attacked by nucleophile. The attacking of the nucleophile on this carbon atom, that is the rate determining step. In the rate determining step, the fluorine atom plays some role. There is one major application of this reaction, that is Sanger's method of analyzing amino acids. Say a protein is like this. I have given only 2 amino acids. This amine, it is free. Similarly, the other end there will be acid. So it can act as nucleophile. What I am going to do, I am going to add a compound, something like this. Now, this fluorine, this carbon atom, it has more positive charge. That can be substituted by nitrogen. So what we get is NH then afterwards it will be the aromatic ring. We get this. Now if I subject this to hydrolysis, this peptide bond will undergo hydrolysis to give OH. So the other bonds also may get cleaved. But I can find out what is the N terminal in this amino acid. Now I have this compound. Since it has aromatic ring, this will be highly UV active. You can separate this, maybe it may be solid also. Then easily you can find out the structure by NMR, and you can find out what amino acid is present in the compound. So that amino acid is nothing but the N-terminal amino acid. We can't find out acid terminal amino acid in the protein, but we can find out N-terminal. Generally, the substrate whatever they give, it will contain NO2. What about other electron withdrawing group? Why only NO2? If you go for ketone, it is very good electron withdrawing group, say acetone, acetophenone, something like this. If I add base Or if I add nucleophile. If I add nucleophile to this, instead of acting as nucleophile and attacking this position, it can attack this position. Or that can take this proton to form enol. So that acts as base. That's why generally aromatic nucleophilic substitution is done with NO2. Similarly, if you go for ester, then the amine, for example, I have taken amine, can displace this. So you may get amide.